A single stone can hold a mystery that defies centuries of explanation. We are surrounded by the silent, staggering work of ancient builders, whose stonework techniques scientists still struggle to explain. From the seamless, mortarless walls to the colossal, laser-aligned blocks of the Giza Plateau, these structures are more than ruins. They are deliberate puzzles left in rock, challenging everything we think we know about history and human capability. By the end of this journey, you will see the ancient world not as a primitive prelude, but as a landscape of profound and unanswered genius. How did cultures across the globe achieve a level of precision that our modern tools can barely measure? What forgotten knowledge allowed them to move mountains of stone as if they were weightless? This exploration is not just about the past. It is about the limits of our own understanding and the thrilling possibility that we have lost something extraordinary. What does it mean when the work of our ancestors feels more advanced than our own? The smooth, cold surface of the stone tells a story of impossible skill. Run your fingers along the joints of an Inca wall in Peru, and you will feel nothing but seamless rock. No gap, no crack, not even the thinnest slip of paper can find purchase. This is not merely good construction. It is a tactile perfection that defies simple explanation, and it forms the very foundation of our mystery. To understand why this work baffles scientists, we must first define what we mean by precision in an ancient context. We are not talking about roughly shaped boulders stacked atop one another. We are talking about interlocking stones, often with complex, irregular polygonal shapes, cut with such astonishing accuracy that they fit together without any mortar at all. Expert stonemason Roger has observed that replicating just one section of such a wall using traditional tools would be, in his words, a lifetime's work for a single wall. So what are the components of this implausible precision? First, the tolerances. The gaps between these massive stones are often less than a millimeter, a level of exactness we associate with modern machine shops, not Bronze Age quarries. Second, the surfaces. Many of these blocks were playing to a condition called optical flatness, meaning they are so smooth and level that light would not bend across them. Third, and perhaps most staggering, is the scale. This millimeter-perfect work was performed on individual blocks weighing dozens, even hundreds of tons, which were then moved across incredible distances and placed with the care of a jeweler setting a diamond. There is a crucial distinction here between stonework that is merely fitted and stonework that appears almost fused. The builders often employed subtle, genius techniques, like cutting blocks with a slight inward concavity. This was not a mistake. It was seismic engineering, allowing the walls to settle and lock during earthquakes. A perfect illustration is the famous 12-angle stone in, a masterpiece of diorite with 12 perfectly interlocking sides. It is less a building block and more a three-dimensional puzzle piece, shaped to match its unique, irregular neighbors on every side. What does this tell us about the minds behind these walls? Their priority was not just stability, but a permanent, unshakable unity between stone and stone. It speaks of a profound, intuitive mastery of geometry, physics, and material science, a mastery we are only beginning to measure, let alone understand. This tactile perfection in Peru is just our starting point, the first clue in a global investigation into a lost world of stone. That same principle of unity reaches its most dramatic expression just above the city. The zigzagging ramparts of fortress are not a wall, they are a statement. Here, limestone blocks the size of buses are locked together in a complex, serpentine pattern that coils across the hillside. This site introduces our first major category of inexplicable technique, the cutting and fitting of massive, irregular polygonal stones. It is the ultimate jigsaw puzzle, but one where each piece weighs over 100 tons and no two connecting edges are the same. The builders did not use standard, rectangular blocks. Instead, they employed what we call the jigsaw puzzle method. Each uniquely shaped block was seemingly custom cut to fit its specific neighbors, with every joint a one-of-a-kind interface. This means the entire wall is a single, interlocked entity. If you tried to remove one stone, the entire section might hold fast because it is supported on all sides by custom-shaped mates. The question is not just how they placed them, but how they shaped them in the first place. Archaeologist Jean Pierre spent years trying to replicate the work using tools the Inca were known to have, like bronze chisels and stone hammers. While he could achieve rough shapes, he concluded that the final millimeter-perfect fitting and the incredibly smooth finishing on hard andesite rock remain largely unexplained by the traditional toolkit. The known tools seem inadequate for such fine, consistent work on such a scale. This forces us to look deeper at the process. One theory involves a lengthy trial and error method using wooden templates. A template could be shaped to match the gap, then taken to the quarry to guide the cutting of a new block. But this still leaves the mystery of the actual cutting and finishing. How do you transform a 200-ton boulder into a precise, multifaceted shape with only stone and bronze? Another clue lies in the stones themselves. Many have mysterious, rounded protrusions on their faces, a feature called knobbing. Some researchers believe these were handles, left deliberately to help workers maneuver the colossal blocks with ropes and levers, and then carefully chiseled off once the stone was perfectly seated. Perhaps the most intriguing idea is the suggestion of a softening agent. Local legends and some researchers point to a plant-based liquid that could have temporarily softened the surface of the stone, making it malleable for shaping before it hardened again into its final, impervious state. While unproven, it speaks to the depth of the mystery. The physical facts are staggering enough. Some stones here weigh over 120 tons. The walls have a slight inward tilt, a deliberate engineering choice for seismic stability, and their foundations are not just laid on the ground, they are cut directly down into the living bedrock, anchoring the fortress to the earth itself. The famous stone of the 12 Angles Inn is merely a small preview, one famous example among hundreds here that exhibit the same impossible standard. So we are left with a fortress that is also a three-dimensional mathematical equation carved in stone. Its very existence questions the simplicity of our historical narrative and hints at a missing chapter in the story of technology. If the tools we have found cannot explain the work, then what tools are we missing from the archaeological record entirely? But the mystery of stone is not confined to massive, singular walls. High on the windswept Bolivian Altiplano, the ruins of Puma present a different kind of puzzle entirely. Here, you will not find colossal, interlocking megaliths. Instead, the landscape is littered with shattered andesite and red sandstone blocks, many of them relatively small, but each one carved with a geometric precision so sharp and so consistent it feels anachronistic. This is not the art of the stonecutter. It is the logic of the machinist. If the Inca walls are a masterful, organic jigsaw, Puma appears to be a kit of standardized, prefabricated parts. The most iconic of these are the so-called H blocks, stones shaped with perfect right angles and symmetrical recesses that look less like ancient artifacts and more like components for a massive, unknown assembly. Their surfaces are not merely smooth. They are flat to a degree that engineer Christopher notes would require a guided cutting tool, not a handheld chisel. The flatness tolerances across these large planes are so minute that light would not warp across them, a condition achievable today only with precision milling machines. How do you achieve such optical flatness on a hard volcanic rock like andesite using only stone and copper tools? The evidence suggests we are missing a fundamental piece of the manufacturing story. Look closer at these stones and you find more bewildering details. Perfectly straight T-shaped channels are cut into the rock with crisp, unwavering edges. Cylindrical drill holes, some as deep as a hand's length, bore straight down with a consistency that implies a stable, rotating drill bit. Some blocks feature intricate patterns of these holes and channels, laid out with geometric precision, as if following a detailed technical blueprint. Then there are the mysterious eye-shaped clamps. Carved recesses in many stones show where metal, likely a copper alloy, was once poured to bind separate blocks together. The metal itself is long gone, likely salvaged centuries ago, but the perfect negative spaces remain, another testament to planned, repeatable joinery. This concept of modularity is what truly separates Puma. The H blocks, with their identical grooves and projections, could have been replicated dozens, even hundreds of times to create a vast, rigid framework. They were not unique puzzle pieces, they were mass-produced components. This shift from unique craftsmanship to standardized manufacturing hints at a completely different technological philosophy. It suggests a system, a planned process of production where stones were cut to a specification, not to fit a specific, existing gap. The ruins today are a catastrophic field of scattered parts, as if a giant's intricate model kit was dropped from a great height. This has led to profound questions about the site's original purpose and the cataclysm that befell it. Were these precision blocks part of a grand, level platform, a complex temple, or something else entirely, a functional structure we can no longer envision? The stones themselves, in their silent, shattered state, argue for a level of technical planning that rewrites our assumptions of what was possible in the deep past. They stand not as monuments of brute force, but as cryptic fossils of a lost industrial logic. From the scattered, machined parts of Puma, we descend into a different kind of precision, one sealed in darkness. The of Saqqara is a subterranean world of silent, staggering intent. Here, in long, echoing tunnels carved deep beneath the Egyptian sand, rest 24 monolithic boxes, each one a sarcophagus carved from a single, immense block of rose granite. Their mystery is not in how they were assembled, but in how they were made hollow. The challenge shifts from fitting stones together to the surgical removal of stone from within. Imagine the task, not of building a box, but of carving one out from the inside of a solid mountain. The granite used here is phenomenally hard, far harder than the bronze or even the iron tools Egyptologists traditionally attribute to this period. To shape it with such control seems to defy the very physics of the known ancient toolkit. The exterior of these coffins is impressive, but it is the interior that holds the true enigma. Each one is a cavern of geometric perfection. The walls are not roughly hewn, they are flat planes, meeting in crisp, sharp 90-degree corners. The surfaces are polished to a mirror-like sheen. When engineer Christopher took laser scanning equipment into these chambers, he made a startling discovery. The interior surfaces of these boxes are flat and parallel to within a few thousandths of an inch. To put that in perspective, that is a level of accuracy we expect from a modern machine shop using guided, powered cutters, not from artisans working with handheld tools over 3,000 years ago. This kind of precision implies something revolutionary, a fixed tool path. It suggests the use of a saw or a grinding apparatus that was stabilized, that could move in a perfectly straight line, removing material with unwavering consistency. How do you achieve such a finish inside a sealed granite box, where your hands and tools have almost no room to maneuver? The logistical puzzles multiply. Each lid is a solid slab of the same granite, weighing over 30 tons. They were not simply placed on top, they were designed to slide. Precision-cut grooves run along the rim of each box and the underside of each lid, acting like ancient rails. This means the builders not only hollowed out the interior with impossible accuracy, they also engineered a seamless sliding mechanism for a door made of stone. Then there is the question of purpose. These are called the Apis bull sarcophagi, and small remains of bulls were indeed found within some of them. But the scale is all wrong. The boxes are massive, each one large enough to hold a small car. The animal remains found inside would have been utterly lost in that vast, polished space. This discrepancy has led many to wonder if their original use was something else entirely, and they were later repurposed for a different ceremonial practice. Perhaps the most telling clue lies in the famous unfinished box, left in a side chamber of the complex. On its surface, you can see the clear, straight grooves cut by a saw. These are not erratic chisel marks, they are parallel lines, evenly spaced, as if made by a blade moving back and forth with mechanical rhythm. Nearby, there are also the unmistakable circular scars of core drilling, where a tubular drill bit bored straight into the granite, leaving a clean, cylindrical hole. The evidence is literally written in the stone. A saw with a cutting edge harder than granite was used here, and it was a saw that did not waver. What powered it? Human muscle alone, pulling on a copper blade with abrasive sand, could not account for the depth, straightness, and consistency of these marks. The force required and the stability needed point toward a level of mechanical advantage or even mechanical power that our textbooks simply do not grant to ancient Egypt. That does not ask us to believe in magic. It asks us to reconsider machinery. It presents a collection of artifacts that, by their very geometry, testify to a process of manufacture that we have yet to fully comprehend. The boxes are not just tombs. They are perhaps the most compelling physical argument for a lost chapter in the story of technology, a chapter written not on papyrus, but in polished stone. The workshop of a master stonemason should be a place of answers, but instead, it presents our greatest dilemma. We have the stones, and we have a collection of tools that archaeology has placed in their hands. Yet when we try to connect the two, the math simply does not add up. This is the tool conundrum, the glaring disconnect between the accepted toolkit and the achieved results. Picture the standard inventory: a bronze chisel, a stone hammer, a copper saw, some abrasive sand, and a set of wooden levers. Now try to use them to carve a perfect 90-degree interior corner inside a solid granite box, or to mill a surface flat to within 1/1000th of an inch. The materials themselves rebel against the task. Bronze is a soft metal, far softer than granite or basalt. Using a bronze chisel on such stone would be like trying to carve a brick with a piece of hard cheese. The tool would deform and blunt almost immediately. Stone hammers, made of a harder rock like dolerite, could pound and fracture the surface, but they are a brutal instrument, utterly incapable of the delicate, controlled removal needed for fine shaping and polishing. Abrasives like quartz sand provided with water can grind stone, but the process is agonizingly slow and almost impossible to control over a large, flat plane without creating dips and waves. Expert experimental archaeologist denies Stock's dedicated years to replicating ancient Egyptian techniques, and while he demonstrated remarkable skill in drilling holes and carving hieroglyphs, the monumental precision of the sarcophagi or the pyramid casing stones remains in a different league entirely. The time required becomes a barrier all its own. Using these methods to achieve the finishes we see would demand not just a lifetime, but perhaps dozens of lifetimes for a single project, a scale of labor that strains historical credibility. The evidence in the stone itself tells a conflicting story. Look at the famous unfinished obelisk in Aswan, still lying in its granite quarry. Here, we see the clear marks of the accepted method, workers pounding trenches with handheld stone balls. The resulting surface is rough, pitted, and chaotic, a world away from the mirror smooth faces of a finished obelisk. If this was the primary technique, where are the transitionary marks, the evidence of this rough work being refined? That evidence is largely absent on the perfect surfaces. Instead, we find other clues, like the straight, parallel saw marks in the, or the clean, cylindrical drill cores found at various sites. These marks speak of a different process, one of guided, mechanical cutting. A handheld copper saw pulled back and forth by two men, even with sand abrasive, cannot produce a cut that is perfectly straight and parallel for its entire length. The human body cannot provide that stability. The force required to make such a cut in granite is immense. This leads to the pivotal question: are we merely missing a few special chisels from the archaeological record, or are we missing an entire methodology, a forgotten principle of machining? Perhaps the tools were not what we assume. Could there have been a process that temporarily altered the stone's properties, a plant-based compound that softened the surface, as some legends suggest? Or were there mechanical aids, lost to time, that provided the stable, repetitive motion we see implied in the stone? The conundrum forces us to look beyond the toolbox on the bench and consider the workshop itself, the very mindset of the builders who saw stone not as an obstacle, but as a material waiting to be precisely transformed. The tools we have found seem inadequate for the task, but what if the task itself was different? What if the ancient builders were not cutting stone at all, but shaping it? This leads us to one of the most provocative ideas in this entire mystery, the theory that a lost chemical or thermal process could have temporarily softened hard rock, making it as workable as wet clay. It is a concept that challenges the very definition of masonry, suggesting the builders were not just artisans, but ancient materials scientists. The most prominent version of this idea comes from materials scientist Joseph, who proposed the theory for the Great Pyramid. He suggests that many of the pyramid's blocks are not natural limestone and hauled, but a form of ancient concrete. In this view, workers would have crushed softer limestone, mixed it with an alkali-rich binder perhaps derived from natron or plant ash, and poured the slurry into wooden molds on site. As it cured, this would harden into a synthetic stone, explaining the block's precise fit and the lack of quarry marks. The science behind is real. They are a class of binders that can create stone-like materials at low temperatures, and they are used in some modern, eco-friendly cements. Proponents point to unusual features, like the presence of air bubbles and organic fibers in some pyramid stones, which you would expect in a cast material but not in solid bedrock. Then there is the phenomenon of vitrification, where stone surfaces appear to have been melted and fused by intense heat. At some ancient sites, like certain hill forts in Scotland, sections of stone walls are found with a glassy, slag-like crust, as if they were subjected to a brief, tremendous fire. Could a controlled application of heat or a chemical agent have been used to slightly melt the surface of adjoining stones, allowing them to be fused together seamlessly upon cooling? This would create joints with no gap at all, a literal welding of stone to stone. Anecdotal evidence adds another layer. There are persistent legends from South America, mentioned by early Spanish chroniclers, about a specific plant whose juice, when applied to stone, could soften its surface for a time, allowing it to be shaped. In modern experiments, researchers have achieved limited success using acid-based solutions derived from local plants on certain types of sandstone, causing a temporary surface softening that makes carving easier. On some ancient stones, you can find strange, scoop-like depressions that do not look like chisel marks. They look more like impressions made in a plastic or semi-soft material, as if someone scooped out a handful before it hardened. While mainstream archaeology remains deeply skeptical, citing a complete lack of direct evidence like chemical residues or tools for such a process, the theory endures because it offers an elegant, if radical, solution to the tool conundrum. It suggests the builders solved the problem of hardness not with harder tools, but by changing the nature of the material itself. This line of inquiry forces us to expand our search beyond chisels and saws and into the realm of ancient chemistry and applied heat. It asks us to consider whether the greatest secret of the stoneworkers was not in their hands, but in their recipes. Even if you could carve a perfect stone, you still had to move it. The leap from workshop to construction site introduces a second, equally baffling dimension of the mystery, a logistical labyrinth where the laws of physics seem to be challenged on a daily basis. Precision in cutting is one thing, but moving a 1,000-ton block of stone is an entirely different order of magnitude. This is not a question of artistry, but of raw, coordinated force, executed with a finesse that modern engineers still struggle to rationalize. The challenge splits into three nearly impossible phases: quarrying the monolith, transporting it across miles of difficult terrain, and finally placing it with pinpoint accuracy, often at a significant height. For a perfect case study, we travel to the valley in Lebanon to the Roman ruins of Baalbek. Here, in the foundation of the great temple of Jupiter, rests a row of 3 limestone blocks so colossal they seem to belong to the realm of myth. Each one is estimated to weigh between 800 and 1,000 tons, They were from a site over a mile away, dragged uphill, and then lifted precisely into place, forming a wall course nearly 20 feet above the ground. To visualize that scale, imagine 3 fully loaded jumbo jets, and then imagine moving them with ropes, logs, and human muscle. The known toolkit of the ancient world appears comically inadequate for such a task. Renowned Egyptologist and engineer Mark has pointed out the fundamental physics problem, friction. Even with an unlimited number of workers pulling on ropes, the force needed to overcome the static friction of a 1,000-ton block on dirt or sand would likely exceed the tensile strength of the ropes themselves. They would simply snap. The ground itself would give way under the concentrated pressure. So how might it have been done? The most commonly proposed method involves a system of wooden rollers on a prepared, lubricated track. This would reduce friction significantly, but introduces new problems. The rollers, made of green wood, would crush under such immense weight unless they were constantly replaced, requiring a vast supply and an army of workers running ahead of the stone to place new logs. Some theorists suggest a different approach, a massive lever and counterweight system, or even a primitive but effective crane using a rotating capstan to wind ropes. Perhaps the most elegant idea is the use of water, flooding a prepared canal or trench to float the stone on a barge, using the buoyancy to negate its weight. Yet each solution demands an astonishing degree of coordination, road construction, and risk management. The precision required did not end with the journey. Lowering a block of this size onto its prepared foundation without cracking it or shattering the stone beneath is an operation of surgical delicacy. A misstep of a few inches would mean catastrophe, wasting years of labor. This speaks to a society with not just manpower, but with exceptional, almost modern project management skills, a deep understanding of collective mechanics, and perhaps a level of patience we can scarcely comprehend. Then there is the ultimate symbol of this logistical ambition, left behind in the quarry at Baalbek. It is known as the Stone of the Pregnant Woman, a single, partially detached block of limestone that dwarfs even the estimates of its weight soar to 1,650 tons. It was successfully cut on 5 sides from the living bedrock, but for reasons lost to time, it was never moved. Its very existence is a statement, a demonstration of a capability so profound that the builders felt confident in attempting it. Standing beside it, one is left with a humbling thought. The moved stones are miracles, but this unmoved stone is perhaps the greater testament, a permanent question mark carved into the earth. It asks us not just how they moved the others, but what they believed they were ultimately capable of. The logistical nightmare of Baalbek suggests that the true lost technology may not have been a single tool, but a complete and sophisticated system of engineering, one that managed to make the unmovable move. The sheer weight of a 1,000-ton stone forces us to consider forces beyond the purely mechanical. What if the solution was not in pushing, but in a kind of controlled resonance, a harmony with the material itself? This brings us to one of the most speculative yet fascinating frontiers of this mystery, the acoustic and resonance hypothesis. It asks a radical question: could sound itself have been a tool for the ancient builders? Across the world, legends whisper of this very possibility. Tibetan texts speak of monks using long trumpets and focused chanting to levitate stones during the construction of monasteries. Ancient Egyptian stories describe priests using specific sounds to make blocks of stone light and easy to move. These are myths, of course, but they persist because they point toward a solution that leaves no physical tool behind, only a memory encoded in story. The core idea rests on 2 principles of physics that are very real. The first is acoustic levitation, a documented phenomenon where sound waves create a pressure field that can suspend and manipulate small objects in mid-air. Modern laboratories use precisely tuned speakers to make droplets of water or tiny particles float. The second is resonant frequency. Every object has a natural frequency at which it vibrates most easily. If you match that frequency with sound energy, the object can enter a state of intense vibration, potentially making its structure more fluid or even causing it to fracture along specific lines. Imagine a skilled singer shattering with her voice, but applied on a monumental scale to shape granite. Could a chorus of voices or a bank of tuned instruments have been used to find and exploit the resonant frequency of a stone, making it momentarily less solid, more malleable? Some researchers point to mysterious sites that seem designed with acoustics in mind. The Hypogeum of in Malta is an underground labyrinth carved from solid limestone. Certain chambers within it are known to produce powerful acoustic effects, amplifying and distorting sound in strange ways. Were these spaces ritual centers, or could they have been part of a forgotten sonic technology? The theory gains a modern, enigmatic parallel in the story of the Coral Castle in Florida. In the early 20th century, a single man named Edward, weighing only 100 pounds, single-handedly carved and erected over 1,100 tons of coral rock. He claimed to have discovered the secret of the pyramids, the method used by the ancient Egyptians to move their stone. He worked alone at night, and when asked how he did it, he would only say he understood the laws of weight and leverage, and the secrets of magnetism and electricity. Some witnesses reported seeing him place his hands on the massive stones and hum. While his methods died with him, his accomplishment stands as a modern testament to the possibility of a lost principle, perhaps one involving harmonic vibration or a manipulation of gravitational fields we do not yet grasp. The acoustic hypothesis is firmly on the fringe of archaeology, criticized for a lack of direct evidence and the immense power required to affect large, dense objects. Yet it serves a vital purpose in this investigation. It pushes us to look beyond the toolkit of levers and chisels and consider the ancient world's potential understanding of energy in its many forms. It suggests that the greatest precision may not have come from forcing stone into submission, but from learning to speak its hidden language. The silent stones of Baalbek and the hum of forgotten acoustics lead us to a profound realization. The ultimate purpose of this staggering precision may not have been to merely build a wall or raise a temple, but to capture the sky itself. Across continents and cultures, the most enduring monuments are not just feats of engineering. They are stone calendars, celestial observatories, and cosmic maps. This is the astronomical alignment enigma, where technical mastery served a higher symbolic function, binding the earth to the heavens with threads of stone and light. The joinery was perfect not just for its own sake, but to ensure the structure would stand long enough and true enough to fulfill a sacred purpose. The most famous example is also one of the most precise. The Great Pyramid of Giza is aligned to the cardinal directions with an accuracy that still astonishes. Its base is oriented to true north with an error of just 3/60ths of a single degree. To understand what that means, picture the face of a clock. That tiny error is like the minute hand being off by less than the width of the hand itself. Achieving this on a construction site covering 13 acres over 4,500 years ago was not an accident. It was the result of sophisticated, pre-planned observational astronomy. How did they do it? And others point to a two-step process. First, ancient surveyors likely used a simple but brilliant tool called a merkit, a notched palm rib with a plumb line, which functioned as a primitive transit for sighting stars. They would have tracked the rising and setting points of a circumpolar star, or in the bowl of the Little Dipper, over the course of a year. By marking the extreme points of its arc on the horizon, they could bisect the angle to find a precise north-south line. A method known as the Indian circle, where a circle is drawn on the ground and perpendicular lines are derived from the shadow of a central gnomon at different times of day, could have refined this further. This celestial datum, this invisible line drawn from the stars, was then translated onto the desert floor with ropes, pegs, and water-filled trenches to create a perfectly level baseline. The entire gargantuan project was built upon this single, astronomically derived line. The precision served a clear cosmological purpose, anchoring the pharaoh's monument eternally to the orderly cycles of the cosmos. This celestial choreography manifests in breathtaking displays of light and shadow. At the Pyramid of At, during the spring and autumn equinox, the setting sun casts a series of triangular shadows down the northern staircase. These shadows connect with stone serpent heads at the base, creating the undulating illusion of a giant feathered serpent slithering down the temple. This effect lasts for only a few minutes, requiring the pyramid's alignment and the proportions of each step to be mathematically perfect. At Stonehenge, the heel stone stands as a solitary sentinel. On the summer solstice, an observer standing at the center of the stone circle would see the sun rise directly over the top of this stone, marking the longest day of the year with a beam of light that travels down the central avenue. These are not vague orientations. They are precise, repeatable astronomical events engineered into stone. Perhaps the most telling clue to the antiquity of this knowledge comes from a windswept, prehistoric site in the Egyptian desert. Playa is a stone circle predating the pyramids by thousands of years. Its carefully placed megaliths align with the rising points of key stars, including those in Orion's belt, and mark the summer solstice sunrise. This demonstrates that sophisticated astronomical observation and the desire to monumentalize it in stone was not a product of advanced civilizations, but rather a driving force behind their very development. The stones of Playa are a blueprint, a conceptual precursor to the grand monuments that would follow. What does this tell us about the builders? Their precision was a means to an end, and that end was a dialogue with the universe. It implies a deep, generational understanding of mathematics, geometry, and cyclic time. It reveals a worldview where engineering and sacred art were inseparable, where the stability of a temple's walls guaranteed the reliability of its celestial prophecies. This was a long-term vision, a project that would outlive its architects by, all to ensure that the sun would always rise in its appointed slot, and the stars would forever find their home in a frame of stone. The perfect alignment of a temple with the stars requires a plan that outlives its architect. This leads us to a deeper, more human layer of the mystery, the transmission of knowledge itself. How does a society without blueprints or engineering textbooks preserve a complex craft across centuries, ensuring that a master's skill is not lost with his passing? This is the software of the ancient world, a system of cultural memory just as sophisticated as the stonework it produced. In many of these cultures, writing as we know it did not exist, or it was reserved for sacred texts, not technical manuals. The Inca, for example, had no alphabetic script, yet they built. Their primary record-keeping device was the quipu, a complex array of knotted cords. While most scholars agree these encoded numerical data for censuses and inventories, some researchers like anthropologist Gary propose they could have represented a much richer information system, potentially even recording narratives, laws, or architectural concepts through the type of knot, its position, and the color of the cord. This hints at a form of three-dimensional, tactile writing specifically designed for the needs of the state. But for the hands-on knowledge of shaping stone, the primary vessel was not a string, but a person. The master-apprentice relationship was the absolute backbone of this transmission. A young initiate would not simply be told how to cut a block. He would spend years watching, fetching tools, mixing abrasives, and performing simple tasks under a watchful eye. Knowledge was passed through meticulous demonstration and relentless practice, embedded in muscle memory and visual intuition. This process was often shrouded in secrecy and ritual. To become a master stonemason was to enter a closed guild or a familial lineage, where techniques were guarded as valuable trade secrets, as precious as the stones they worked. This secrecy ensured quality control and maintained the social status of the craft, but it also made the knowledge incredibly fragile, vulnerable to social upheaval or the sudden loss of key individuals. Ritual and myth played a crucial role as mnemonic devices. The stories of gods shaping mountains or heroes moving stones were not mere fables. They were symbolic containers for practical principles. A song about a journey might encode the logistics for moving a megalith, its rhythm mirroring the pulling cadence of work teams. Ceremonies could reinforce geometric principles through dance patterns or the layout of ceremonial grounds. This embedding of technical knowledge within culture made it resilient, part of the living fabric of the community rather than words on a perishable page. There is also strong evidence for the use of physical models and standardized measurement. In Egypt, exquisitely detailed scale models of buildings and even entire quarries have been found, used for planning and instruction. The Egyptian royal cubit, a standardized length measure based on the forearm, was meticulously maintained and used across the kingdom for ensuring that a blueprint in Thebes could be executed perfectly in Aswan. This points to the likely existence of formal schools for architects and master builders attached to major temples or royal courts, where this standardized knowledge was curated and advanced. We see a powerful parallel later in the medieval European cathedral builders. The master masons of the Gothic era operated through lodges, secretive fraternities that passed down complex secrets, like the techniques for plotting a vault's ribs or calculating a flying buttress's angle, through initiation rites and symbolic teaching tools. Their plans were often full-scale layouts, called tracing floors, drawn in plaster on a dedicated floor where the master could walk his apprentices through the design. This brings us to the ultimate test case for knowledge transmission. Over 12,000 years ago, hunter-gatherers carved, transported, and erected 20-ton limestone pillars with precise iconography. How did a literate, agrarian society coordinate such a project and pass the necessary skills down through generations? The answer may lie in the site's own purpose. It was not a settlement, it was a ritual center, a gathering place for scattered groups. The very act of building it, the shared labor and the oral traditions that grew around it, could have been the engine that preserved and refined the technical knowledge. The site itself was the school, and the process of its creation forged the cultural bonds needed to sustain the craft. This perspective shifts our understanding. The precision in the stone is not just a testament to individual genius, it is the fossilized imprint of a sustained, collective intelligence, a chain of teaching and learning that remained unbroken long enough to achieve the impossible. When that chain was finally severed, whether by invasion, climate change, or a shift in beliefs, the techniques faded into legend, leaving behind only the stones to whisper of the system that created them. These scattered whispers of knowledge, from apprentice to master, form a chorus when heard from a global perspective. A map of the ancient world reveals a startling pattern, a constellation of precision stonework that spans continents and oceans with no apparent lines of connection. From the submerged terraces of in Japan to the colossal, sun-warmed walls of in Peru, cultures who never knew each other's names arrived at eerily similar solutions. This is not a story of one isolated genius, but a recurring human signature etched in granite and limestone. When we compare these sites side by side, common threads emerge that deepen the central mystery. Why did builders in Mycenaean Greece and the Inca Empire, separated by thousands of miles and years, both choose to construct trapezoidal doorways, a shape renowned for its incredible seismic stability? It is a logical engineering solution to be sure, but the consistency is striking. Look at the use of stone bosses, those unexplained knobs left protruding from massive blocks. We find them in the quarries of ancient Egypt, on the foundations at and on the megaliths of Baalbek. Were they simply handles for maneuvering, or do they hint at a shared, specialized technique for moving monoliths that we have yet to decipher? The drive to create perfectly flat, optically true surfaces appears as a global obsession. The mirror finish on the granite boxes of the finds its echo in the polished andesite of Puma and the planed surfaces of certain Japanese tombs. This pursuit of flatness goes beyond mere aesthetics. It speaks to a value placed on geometric perfection, on creating a plane that interacts flawlessly with light and plumb line. Perhaps the most visually compelling parallel is the mastery of the sphere. The famous, nearly perfect stone spheres of Costa, some weighing over 15 tons, were shaped with such symmetry that their purpose remains unknown. Intriguingly, similar, perfectly spherical stone balls have been discovered at sites in Bosnia, crafted from a different rock, but demonstrating the same formidable control over form. Creating a perfect sphere from hard stone is a geometric challenge of the highest order, requiring consistent measurement from a central point in all directions. That two cultures would invest such effort into this specific, non-utilitarian shape is a profound coincidence. So how do we explain these global patterns? One compelling answer is independent innovation. Faced with the universal challenges of earthquakes, the desire for permanence, and the physical properties of stone itself, brilliant minds in different times and places may have simply converged on the most effective solutions. Polygonal masonry locks tightly during tremors. A mortise and tenon joint is a supremely strong way to connect two pieces of material, whether wood or stone. This theory of convergent technological evolution suggests that the logic of the material guided disparate cultures to similar endpoints. Yet, the sheer sophistication and the repetition of very specific, non-obvious techniques, like the precise astronomical alignments found from Giza to Stonehenge to the Mississippian mounds, give pause. Could there be a deeper, older root? Some researchers point to the possibility of a common ancestral knowledge, a foundational set of geometric and engineering principles that diffused across the globe in the deep mists of prehistory, carried by migrations long forgotten. This is not to suggest ancient astronauts or a single supercivilization, but rather to acknowledge that human history is far longer and more interconnected than our conventional timelines often allow. The last great ice age lowered sea levels, creating land bridges and altering coastlines, potentially enabling exchanges of ideas across distances we now see as impassable. Whether through independent genius or a faint, shared heritage, the global pattern tells us one thing for certain. The drive to shape stone with impossible precision was not an anomaly. It was a fundamental expression of human aspiration, a widespread testament to a forgotten relationship between our ancestors and the very bones of the earth. This recurring signature asks us to look deeper, to see these sites not as isolated wonders, but as chapters in a single, sprawling, and still unwritten story of our past. Water is the silent architect behind many of these stone marvels. The most enduring ancient sites are not just placed near water, they are engineered to converse with it, to channel its flow with a precision that suggests a profound, practical motivation for their craft. This connection reveals a compelling theory that the relentless drive for millimeter-perfect joinery may have been born not from a desire to impress the gods, but from the urgent need to control a vital resource. When your survival depends on capturing every drop of rain or directing a mountain spring across miles of terraced fields, a leak is not an imperfection, it is a catastrophe. This hydraulic imperative could have been the ultimate proving ground for ancient engineering. The Inca provided in this fusion. A network of stone canals and fountains, fed by a natural spring over half a mile away, still functions flawlessly today. The gradient is so carefully calculated that the water flows at a constant, gentle pace, never eroding the channels. Each joint between stones in these waterways is so tight that even under pressure, water cannot find a path to escape. Hydrologists studying these systems note that achieving this requires more than careful placement. It demands an understanding of hydrostatic pressure, of how water seeks the weakest point. The builders had to create channels with consistent cross-sections and smooth interiors to maintain flow and prevent sediment buildup, a task that implies advanced surveying and a standardized unit of measurement. This water management extended to monumental scales. Consider the mysterious in Egypt, a structure built at a level far below the nearby temple of Seti I. Its central hall is surrounded by a moat, and its architecture, with massive, undecorated granite pillars, feels more like a functional hydraulic engine room than a temple. Some researchers, like archaeologist John West, have argued its design suggests it was once a flowing, active water feature, perhaps part of a symbolic representation of the primordial waters of creation or a sophisticated device for groundwater control. The techniques developed for water were remarkably consistent. To seal joints, cultures from Rome used natural sealants, pouring molten lead or layering asphalt between stones to create a permanent, flexible gasket. They carved parabolic overflow channels into spillways, a shape that efficiently manages varying water volumes. Perhaps the greatest testament to this hydraulic precision is the Granite, an underground aqueduct. Originating in ancient Persia, these tunnels were dug with a gentle, unwavering slope for miles, often through solid rock, to bring water from mountain aquifers to arid plains. Maintaining that precise grade over such distances, using only sighting rods and water levels, was a geometric triumph that sustained entire civilizations. This practical need may even explain some of the stone shaping methods themselves. The water cutting theory proposes that directed, high-pressure jets of water mixed with an abrasive sand could have been used to slice through granite. It is a method used in modern quarrying, and it leaves behind characteristically smooth, flowing surfaces free of tool marks. While evidence for its ancient use is circumstantial, the concept is compelling. It turns water from a passive resource into an active tool, a liquid saw capable of sculpting the hardest stone. A perfect illustration of this hydraulic artistry is found in the Temple of the Sun. Intricate stone basins are carved directly into the monumental pink porphyry blocks. These basins are interconnected with channels, and they align so precisely with seasonal water flows that during certain times of year, they would have filled and drained in a carefully orchestrated sequence, possibly for ritual cleansing or astronomical observation. They are completely leak-proof, a testament to a craft refined by necessity. This perspective changes the narrative. The seamless joints and the polished surfaces of them begin to look less like abstract religious devotion and more like the spillover of a highly refined, practical technology. The mastery needed to make a stone conduit watertight is the same mastery needed to make a wall earthquake-proof or a sarcophagus lid slide seamlessly. It suggests that the quest for precision was, at its heart, a response to the environment, a dialogue with the forces of nature where the penalty for error was drought or flood. The stones were not just placed, they were engineered to hold something far more precious than weight. They were built to hold life itself. The true test of any structure is not the weight it holds, but the motion it survives. In the earthquake-prone belts of the Andes and the Mediterranean, ancient builders left behind a paradox: structures that have endured thousands of years of violent tremors, while modern concrete buildings around them have crumbled into dust. The secret to this incredible longevity lies not in defying the Earth's movement, but in a profound, elegant cooperation with it, a principle engineered directly into the precision of the stone itself. At the heart of this seismic genius is the dynamic, flexible nature of dry stone polygonal masonry. Picture a rigid mortared wall during an earthquake. It is a single, brittle unit, and when the ground shakes, that whole unit tries to move as one. The mortar, meant to bind, becomes a point of failure, cracking, and crumbling until the wall collapses. Now, envision an Inca wall. It is not a single unit, but a community of individual stones, each one uniquely shaped and interlocked with its neighbors. There is no mortar to glue them rigidly together. When the ground shakes, these stones can do something remarkable. They can shift, rotate, and settle against one another. They are not fighting the earthquake, they are dancing with it, absorbing and dissipating the energy through countless tiny movements along their intricate joints. Engineering studies, including rigorous shake table tests conducted by the University of Tokyo, have physically demonstrated this behavior. Models of Inca-style walls were subjected to simulated quakes, and the blocks were seen to sway and rock, settling back into place once the shaking stopped, often in a slightly different but still perfectly stable configuration. This resilience is achieved through several deliberate design principles. First, notice the slight inward lean of many ancient walls. This battering is not an optical illusion or settling. It is a calculated choice that lowers the center of gravity and encourages the wall to settle inward onto itself during a tremor, becoming more stable, not less. Then, look for the strategic use of L-shaped keystone blocks. These stones, with a long leg and a shorter foot, are often placed at critical corners or intersections. Their unique shape acts as a three-dimensional lock, bracing the structure in multiple directions and preventing sections from sliding apart. The distribution of weight is also masterful. Larger, heavier blocks are typically placed at the base, with gradually smaller ones above, creating a stable, tapered profile. But perhaps the most ingenious feature is the very irregularity of the joints. In a wall of uniform rectangular blocks, a seismic shock can create a straight, continuous crack that propagates up the entire structure, a single line of failure. In polygonal masonry, every joint is a unique zigzagging interface. A crack starting at one point cannot travel in a straight line. It is forced to meander, losing energy at every turn until it simply stops. This design finds a startling parallel in our most advanced modern seismic technology, base isolation. In skyscrapers and hospitals today, engineers install flexible bearings or pads between a building's foundation and its superstructure. These devices allow the ground to move independently beneath the building, isolating the structure from the most violent shocks. The ancient walls achieve a similar effect through their intentional looseness. Each stone is, in a sense, its own isolated unit, able to move minutely within the collective. A powerful illustration of this principle stands in the heart of. The Church of Santo was built by Spanish colonists directly on top of the exquisitely curved walls of the Inca, the Temple of the Sun. Over the centuries, major earthquakes have repeatedly damaged and collapsed the colonial church above, requiring costly rebuilds. Yet each time, the flawless Inca stonework foundation beneath has remained utterly unmoved, a steadfast platform upon which the fragile later construction rests. This is not a coincidence, it is a demonstration. The precision of those joints, the subtle concavity of each stone face, the interlocking puzzle of it all, was not merely for aesthetic grandeur. It was a sophisticated, life-saving structural system born from empirical observation. Generations of builders learned, through trial and error across centuries, how to build in conversation with a volatile earth. Their legacy is a stone testament to the idea that true strength lies not in rigid resistance, but in intelligent, graceful adaptation. That same seismic resilience speaks to a deeper truth. The perfect joint was never just a feat of engineering, it was a profound statement written in a language of stone. For the cultures that achieved it, this precision was a multidimensional act, weaving together the spiritual, the political, and the cosmic into a single, enduring symbol. To shape a stone with such care was to engage in a dialogue with eternity itself. Anthropologist Mary Helms notes that in many ancient societies, the act of transforming raw, chaotic nature into a refined, cultural object was a sacred endeavor. The immense difficulty of the work, the years of labor and the mastery required, did not detract from its value, it amplified it. The struggle itself consecrated the stone, elevating it from mere material to a vessel of meaning. A ruler who commissioned a wall that would stand for 10,000 years was not merely building a fortress. He was etching his legacy and his civilization's cosmic order directly into the bones of the earth. The seamless joint, therefore, became a powerful metaphor. In a kingdom comprised of diverse peoples and distant territories, a wall where every stone fit perfectly, with no gap or weakness, represented the ideal of a seamless, unified state. It was a physical manifestation of social and political harmony, where every individual, like every stone, had a unique and essential place in an unshakable whole. This symbolism extended to the very interaction with light. The obsessive polishing of granite in Egypt or andesite in the Andes was not purely aesthetic. In solar cults, a surface that could catch, and reflect the rays of the sun with mirror-like brilliance, transformed the stone into a captured fragment of the divine. The pyramids casing stones, gleaming white under the desert sun, were not just a dazzling sight. They were a declaration that the pharaoh's monument communed directly with the solar deity Ra. This reverence for material extended to the choice of stone itself. Builders often selected specific types for their symbolic properties. The red sandstone of certain Hindu temples was chosen for its association with life and purity. The unique green hue of serpentine or jade in connected structures to concepts of fertility, water, and sacred authority. Even acoustic properties were considered. Some chambers in ancient temples exhibit remarkable sound qualities, where a whisper at one end can be heard clearly at the other, potentially designed to amplify ritual chants or create an aura of mystical presence during ceremonies. The process of obtaining the stone was often as ritualized as its placement. Historical accounts and ethnographies suggest that quarrying was frequently preceded by offerings and prayers, asking permission from the earth to take its substance. The act of cutting the first block or laying the foundation stone was a major ceremonial event, involving priests, blessings, and sometimes even symbolic sacrifices to ensure the favor of the gods and the stability of the work. This holistic view is beautifully embodied in the Japanese art of the precise stone paving found in Zen gardens like Kyoto's. Here, stones are fitted together with such care that the seams are nearly invisible, creating a rippling, interconnected tapestry. The purpose is not structural, but meditative. The perfection of the fit, the flow from one stone to the next, is meant to quiet the mind and visually represent the interdependent nature of all existence. Every stone is an individual, yet it only finds its true meaning in relation to the whole. This brings us to the core revelation. When we look at a seamless Inca wall or a polished Egyptian sarcophagus and ask how they did it, we are asking a technical question. But to understand why they did it, we must learn to read the symbolism encoded in the join. The immense, generation-spanning effort was not a misallocation of resources. It was an essential investment in constructing reality itself, in aligning human society with the perceived perfection of the cosmos. The struggle to explain the technique is therefore also a struggle to comprehend a worldview where such precision was the highest form of prayer, politics, and philosophy, all expressed in the silent, eternal language of stone. The undeniable truth of the stone has met the determined skepticism of the modern laboratory. To truly test the boundaries of the possible, teams of engineers, stonemasons, and archaeologists have rolled up their sleeves, trading theories for calloused hands and sweat. Their mission is deceptively simple: to recreate the ancient wonders using only the tools and materials we believe were available at the time. These are not thought experiments, they are physical trials, and their results are a humbling ledger of our own limitations. The central revelation from every attempt is a profound gap, a chasm between what we can achieve with the accepted toolkit and what the ancients accomplished on a monumental scale. It is a gap measured in time, in efficiency, and most tellingly, in the final, flawless precision of the finished product. Take the ambitious experiment led by Egyptologist Mark. He assembled a team to build a small, 6-meter-tall pyramid using only copper chisels, stone pounders, and wooden sledges. The project provided invaluable insights into the logistics of quarrying and moving stone. Yet, after weeks of backbreaking labor, the team's pyramid, while recognizable, lacked the breathtaking exactness of Giza. Their blocks were rough, their alignments good but not perfect. The experiment made one thing starkly clear: the sheer, staggering volume of human effort required was almost beyond modern comprehension, and even that immense effort could not replicate the original's iconic perfection. Other projects have focused on specific, Herculean tasks. Teams have tried to move a 40-ton obelisk using nothing but ropes, wooden rollers, and a prepared earthen ramp. The coordination required was immense, with dozens of workers pulling in unison to the rhythm of chants, inching the colossal stone forward. While successful, the process was agonizingly slow and fraught with risk. A single snapped rope or a crushed roller could mean disaster. The physical toll on the participants was severe, a stark reminder of the human cost embedded in these ancient monuments. The challenge of shaping the stone itself has proven even more daunting. In attempts to work granite, modern masons have used dolerite pounders, the hard stone hammers attributed to the Egyptians. The process is brutally simple. You pound the surface until it fractures, then pound again. It is effective for rough shaping, but to achieve a smooth, flat plane or a sharp interior corner is a different matter entirely. The work is excruciatingly slow, and controlling the final form with this method is extraordinarily difficult. For the intricate polygonal masonry of the Inca, experimenters have tried the wooden template method. They would shape a template to fit a gap, take it to a new stone, and attempt to carve a matching face using stone tools and abrasives like sand. While they could get a rough fit, achieving the seamless, paper-thin joint of the originals consistently eluded them. The fine finishing alone, that final millimeter of perfection, could take weeks for a single interface. Perhaps the most public-facing of these endeavors was the television series Secrets of Lost Empires, which took on Stonehenge and Inca walls. In each episode, teams of experts devised ingenious methods using period technology. They successfully erected a Stonehenge using a frame and a massive counterweight, and they managed to move and place a ton Inca-style block. Yet, time and again, the conclusion was not a triumphant "we solved it," but a deepened respect. The modern teams, with their advanced planning and safety protocols, still struggled with the sheer physicality and precision required. They ended not with definitive answers, but with admiration for the ancients' mastery and an acknowledgement of the many plausible methods that could have been used, none of which fully closed the case. These replication efforts force a sobering admission. They demonstrate that the known methods are possible in theory. A block can be moved, a stone can be shaped. But they also reveal that these methods seem implausibly slow, inefficient, and inconsistent for the scale and quality of work we see dotting the globe. The experiments highlight a missing variable in our equation. Either we are overlooking a key piece of technological ingenuity, a clever trick or tool that has vanished from the record, or we must confront a more profound idea. Perhaps the ancient builders possessed a cultural capacity for sustained, generational effort and a pinnacle of artisan skill that operates on a timescale almost foreign to our modern, time-pressed world. Their patience was not merely a virtue, it was the foundational technology itself, a resource we have largely depleted. The weight of these replication failures creates a vacuum, a space where mainstream explanations feel incomplete. Into that void flow ideas of a different magnitude, theories that rewrite the very timeline of human achievement. This is the territory of lost civilizations and forgotten golden ages, a controversial but persistent undercurrent in the search for answers. While traditional archaeology builds its case layer by careful layer, other voices propose a more dramatic narrative, one of a cataclysm that reset the board, leaving only the most indestructible pieces behind. Authors like Graham present a sweeping hypothesis, a lost, advanced civilization he calls the mother culture of antiquity. This society, possessing sophisticated knowledge of astronomy, engineering, and agriculture, is said to have flourished before a global catastrophe, perhaps a comet impact or rapid climate shift, around 12,000 years ago at the end of the last ice age. Survivors of this event, according to the theory, scattered across the globe, carrying fragmented seeds of their knowledge to the emerging cultures of Egypt, Mesopotamia, and the Americas, explaining the sudden, seemingly miraculous appearance of advanced techniques. Proponents point to a constellation of tantalizing clues. They highlight the uncanny astronomical alignments of ancient sites that seem to point not to the skies of 4,000 years ago, but to the celestial map as it appeared over 10 earlier. They point to the universal flood myths found in hundreds of cultures worldwide, from the Epic of Gilgamesh to the story of Noah, seeing them not as mere allegory, but as a collective memory of a real, planet-altering event. The argument extends to the very stones, asking if the precision we see is not the product of early experimentation, but the faded echo of a much older, higher standard. A focal point of this debate is the Great Sphinx of Giza. Geologist Robert observed what he interprets as weathering patterns on the Sphinx enclosure, erosion that appears vertical and flowing, more consistent with prolonged, heavy rainfall than with wind and sand. Since the Giza Plateau has been arid for the last 5,000 years, and others suggest the Sphinx could be far older, perhaps dating back to a time when the climate of Egypt was much wetter, pushing its origin back thousands of years before the reign of the pharaohs traditionally associated with it. Mainstream Egyptologists counter this vigorously, citing other geological studies that attribute the weathering to wind, humidity, and the effects of ancient quarrying. They point to the complete absence of any archaeological evidence, no tools, no pottery, no settlement remains, that would support the existence of such a sophisticated society in that remote era. This is the core critique, the evidential silence. If a globe-spanning, monument-building civilization existed, where are its cities, its tools, its everyday artifacts? The archaeological record shows a gradual, traceable progression of human technology, not a sudden inheritance from a vanished master race. Critics also question the concept of technological devolution, the idea that knowledge was lost and societies regressed. They argue that cultural knowledge can indeed be lost, as we have seen with the Roman concrete recipe or Damascus steel, but the complete erasure of an entire civilization's material culture, while leaving its most massive and difficult projects intact, strains credibility. Yet, even in dismissing the specifics, one must acknowledge the legitimate questions that give these fringe theories their enduring power. They emerge from the genuine, palpable gaps in our understanding, from the sheer improbability that whispers from every seamless joint. They challenge the comfort of orthodoxy and force a re-examination of assumptions. Engaging with these ideas, even from a skeptical standpoint, serves a vital purpose. It reminds us that the mystery of the stones is not a trivial puzzle, but a profound catalyst. It pushes us to look deeper, to question more rigorously, and to remain open to the possibility that the human story is longer, stranger, and more resilient than any single narrative can contain. The stones do not speak of aliens or Atlantis, but they do speak of a capability that continues to elude our full comprehension. In that silence, every theory finds its beginning. The standard explanations feel like they should be enough. Given enough hands, enough time, and enough determination, humanity can achieve the impossible. This is the core of the mainstream archaeological view, a powerful and often convincing defense of human ingenuity. It is a model, one that sees these monuments not as sudden miracles, but as the logical pinnacle of generations of accumulated knowledge, relentless social organization, and patient trial and error refinement. The argument is compelling because it is built on tangible evidence. At the Great Pyramid, we find the remains of worker barracks, evidence of massive bakeries, and logistical records that speak of a state capable of marshaling thousands of individuals into a coordinated, decades-long project. We have found the stone pounders in the quarries, the copper chisels in the workshops, the sledges, and the remnants of what could be transport roads. Egyptologist Mark, through his experimental archaeology at Giza, has shown how these tools could be used effectively, not with magic, but with immense, sustained effort. The progression is clear in the record, from the small, rough-step pyramids of the early dynasties to the polished perfection of Giza, a visible arc of learning across a century of royal ambition. For the movement of megaliths, the explanation points to simple physics mastered on a grand scale. The spiral ramp for the pyramids, the log rollers and lubricated sledges for the stones of Baalbek, the lever and fulcrum systems, all are demonstrated principles that, when scaled up with enough human power, become plausible. The key ingredient in this view is not a secret tool, but a secret resource, time. A society willing to dedicate generations to a single project operates on a timescale we struggle to comprehend. A master mason might spend his entire life perfecting the finish on one section of one wall, teaching his son to do the same. This generational patience, combined with the sheer force of numbers, becomes the invisible technology. The official explanations for specific sites follow this logic. The pyramids were built using a combination of straight and spiral ramps, with internal ramps proposed for the final stages. The stones of Baalbek were dragged on a prepared causeway using ropes, rollers, and the coordinated pull of hundreds of oxen and men. The polygonal walls of the Andes were shaped through meticulous pounding with harder stones and finished by grinding with sand and water, a process that could take months for a single block. This perspective sees the ancients as fundamentally like us, just with a different set of priorities and a profound cultural capacity for long-term effort. Yet, for all its evidence and logic, this model hits a wall of quiet resistance in the mind of the observer. The shortcomings are not in the theory, but in the translation from theory to the physical reality we can touch. The mathematical precision remains a stumbling block. We can understand how you might drag a 1,000-ton block, but how do you lower it into place with an error margin of less than a millimeter? We can accept that sand can grind stone flat, but how do you achieve optical flatness over a surface the size of a car door without creating waves or dips? The known tools can create the rough form, but the final, flawless finish on the hardest stones often lacks the transitional marks, the scratches and gouges, that such a brutal process would inevitably leave behind. It is the absence of evidence where we most expect it. On the finest works, like the interior of the boxes or the faces of the Puma blocks, the tool marks vanish, replaced by a machine smoothness that feels out of place. The physics of moving the largest megaliths also strains the model to its breaking point. The static friction of a 1,650-ton stone, like the one in the Baalbek quarry, presents a force so immense that known ropes would snap and any wooden roller would simply pulverize under the load. The standard explanations require additional, unproven technologies, like continuously replaced reinforced rollers or impossibly strong cables, just to make the basic mechanics work. This creates a tension at the very heart of the mystery, a respectful debate between two ways of seeing the past. One side sees our ancestors as brilliant, patient engineers who use the tools we have found to their absolute limit. The other wonders if the tools we have found are merely the everyday implements, and that the specialized technology for the finest work, perhaps guarded and secretive, has been lost entirely. Acknowledging the limits of current explanations is not an attack on science or a descent into fantasy. It is an honest admission, a necessary humility. It is the space where curiosity lives, the fertile ground between what we can prove and what we can plainly see. The stones stand as a challenge not just to our tools, but to our timelines, our assumptions about cultural evolution, and our understanding of what human collaboration can truly achieve when driven by a purpose that spans centuries. To admit we do not have all the answers is to keep the door to history open, allowing for the possibility that the story is even richer and more surprising than we have yet dared to believe. The smooth, machined surfaces of the past are now being read by the most precise eyes we have ever possessed. We have entered a digital age of discovery, where our most advanced technologies are not used to build new wonders, but to measure the old ones with a scrutiny that borders on the microscopic. Lasers, LiDAR, and three-dimensional modeling are our new archaeological tools, not for moving stone, but for quantifying its secrets. This technological lens is providing hard data, turning subjective awe into objective, measurable mystery. The process begins with light. LiDAR, which stands for light detection and ranging, works by firing millions of laser pulses from an aircraft or drone toward the ground. Each pulse bounces back, and by measuring the time it takes, a computer can build a stunningly accurate three-dimensional map of the surface, stripping away layers of jungle canopy or sand to reveal the geometry hidden beneath. This technology has revolutionized exploration, uncovering entire lost cities in the dense jungles of Cambodia and Guatemala, cities that were invisible to generations of explorers on the ground. It reveals not just structures, but the very footprint of ancient civilization, from roads and canals to terraced fields, all etched into the digital landscape. On a more intimate scale, ground-based three-dimensional laser scanners perform a similar magic on individual structures. A scanner placed at a site like the or spins, capturing billions of data points, creating a point cloud model accurate to within a single millimeter. This is not a photograph, it is a perfect digital twin. Researchers can then manipulate this model in ways impossible with the physical stone. They can calculate the flatness of a surface to 1/1000th of an inch, measure the angles of joints, and analyze wear patterns across centuries. When engineer Christopher Laser scanned the interior of this granite boxes, he wasn't relying on a trained eye. He was gathering irrefutable data that confirmed the surfaces were flat and parallel to a degree achievable only with guided machinery. The digital model becomes a laboratory. Experts can run finite element analysis, simulating earthquakes to see exactly how stress flows through a polygonal wall, revealing why it dances while a rigid wall would shatter. They can strip away layers digitally, attempting to reverse engineer the construction sequence block by block. Perhaps the most comprehensive application of this is the Giza Plateau Mapping Project. Using a suite of technologies, including laser scanning and photogrammetry, which builds models from thousands of overlapping photographs, the project has created a hyper-detailed digital record of the entire pyramid complex. This scan has revealed subtleties invisible before. It shows that the Great Pyramid's base is not a perfect square, but has a slight concavity to each side, a deliberate feature that may have helped the casing stones settle more securely. Scans of the interior have mapped the precise misalignments of the so-called air shafts, suggesting they were adjusted during construction, a story of on-the-fly problem-solving written in stone and now readable in data. Ground-penetrating radar adds another dimension, sending pulses into the earth to reveal voids and anomalies. It was this technology that suggested the now famous discovery of a large void above the Grand Gallery in the Great Pyramid, a hidden space whose purpose remains a tantalizing unknown. The implications are profound. This digital scrutiny is not closing the case on ancient precision, it is opening new, more detailed chapters of the mystery. We are no longer just saying the work is precise, we can now state exactly how precise, and the numbers are often staggering. It allows us to move beyond speculation and test theories with digital experiments. Could a team of 200 men using ropes have moved that block? A physics simulation can provide a data-driven estimate. Could a stone hammer have created this surface finish? A microscopic analysis of the digital surface texture might show tool marks inconsistent with pounding. The technology also democratizes discovery. A three-dimensional model of a remote site can be studied by experts across the globe, allowing for collaboration on a scale never before possible. Yet, for all its power, the digital age presents a humbling paradox. The more precisely we measure, the more impressive the ancient achievement becomes. The data provides facts, but not the blueprint. It deepens our appreciation while simultaneously widening the gap between what we can measure and what we can explain. We are left with a crystal-clear, millimeter-perfect digital model of an impossibility, a mystery rendered in perfect, undeniable detail. Every fingerprint left on a seamless stone is a tiny, irreversible erosion of history. The very human desire to touch this impossible perfection, to feel the cold surface of a mystery, becomes its own slow threat. We stand now at a critical juncture, where the objects of our deepest curiosity are endangered by the attention they command. These sites are not static museum exhibits, they are living, fragile landscapes caught between a rising tide of visitors and the relentless pressures of a changing world. The ethical dilemma is profound. How do we protect the physical evidence of a mystery we have not yet solved? The conflict is between accessibility and preservation. Opening a site to the public funds its maintenance and shares its wonder with the world. But each footstep, each resting hand, introduces wear. The oils from human skin, over decades, can darken and degrade even the hardest granite. At places like the treasury in Petra or the interior chambers of the Great Pyramid, the cumulative breath of millions has altered humidity levels, encouraging salt crystallization within the stone, a process that slowly forces the surface to flake away. Beyond tourism, environmental assaults are mounting. Acid rain, born from distant industrial pollution, dissolves the delicate surface of limestone monuments. In Egypt, the Sphinx endures not just the mythical passage of time, but the very real chemical weathering from Cairo's smog. Climate change introduces new volatility, with more intense rainfall events triggering landslides that threaten foundational terraces, as seen on the vulnerable slopes surrounding. Even the seismic resilience of these structures has its limits. Every tremor, no matter how well absorbed, adds a minute cumulative stress to stones that have already endured thousands of years. The task of preservation is therefore a race against invisible forces. Conservators employ techniques as sophisticated as the original construction might have been. They create controlled microenvironments, using subtle ventilation systems to stabilize temperature and humidity within a tomb. They deploy invasive monitoring, with networks of tiny sensors that measure tilt, vibration, and crack propagation, sending silent alerts long before human eyes would see a problem. One of the most controversial tools is the practice of reassembling a fallen structure using its original pieces, often with a neutral, modern material for support. This can make a site comprehensible to visitors, turning a field of scattered blocks back into a recognizable temple. But it raises a thorny ethical question: where does preservation end and reconstruction begin? This debate becomes intensely personal when applied to the dry stone walls of the Inca. Should conservators repoint the joints with modern mortar to prevent water infiltration? Doing so might save the stones from frost damage, but it would also fundamentally alter the structure's dynamic, seismic flexibility, gluing together a wall that was designed to dance. The answer increasingly lies not in a universal rule, but in deep collaboration with local communities who are the inheritors and traditional stewards of these places. Their ancestral knowledge of the land, its weather patterns and seasonal rhythms, is an invaluable layer of data. When communities are partners in preservation, the work gains a cultural continuity, protecting not just stones, but the living memory they hold. The ongoing efforts illustrate this delicate balance. To manage the impact of over 1 million visitors a year, authorities have implemented strict ticketing systems, designated walking routes, and time slots for entry. Repairing damage from landslides involves painstaking work, where new stone is from the same source as the original, shaped with a blend of traditional and modern tools, and set in a way that respects the original engineering, all while the site remains open to the world. This is the core of the preservation imperative. It is an act of humility. We are caretakers of a question we cannot answer. Our responsibility is to ensure these precise stone puzzles survive, intact and unaltered, for the generations of scientists and engineers who will follow us. They will bring tools of analysis we cannot yet conceive, perhaps able to read the faintest chemical residue of a lost tool or model stress patterns in ways that reveal the builder's exact sequence of choices. The mystery can only be solved if its physical language is preserved. To lose even a single, perfectly fitted stone to carelessness or decay is to burn a page from the only instruction manual we have, a manual written not in words, but in the silent, enduring grammar of rock. The smooth granite beneath our fingers feels less like a solved equation and more like a mirror. We see our own reflection in its perfection, and the image it returns is one of profound, unsettling wonder. This is the true power of the stone, a psychological gravity that pulls us in long after the technical explanations fall short. Why does this specific mystery captivate millions, fueling endless documentaries and late-night internet rabbit holes? The answer lies not in the joints of the stone, but in the architecture of our own minds. Confronting work that appears to surpass our modern capabilities triggers a deep cognitive dissonance. Our entire cultural narrative is built on a foundation of progress, a steady upward climb from primitive beginnings to our current, technologically dazzling peak. These stones stand as silent, stubborn counterpoints to that story. They introduce a plot hole in the epic of humanity, and our brains are wired to seek resolution for such gaps. The emotional response is a complex mix, what philosophers of the 18th century termed the sublime, an awe that borders on unease. We are drawn to the vast scale and incomprehensible skill, feeling both inspired by the achievement and strangely diminished by it. This is the core of the so-called ancient astronaut feeling, though it has little to do with literal visitors from the stars. It is the humbling sensation that the people of the past might have possessed a different kind of sophistication, one we have not just forgotten, but perhaps can no longer even fully perceive. Their mastery whispers of a different path, a road not taken in our relentless pursuit of digital and mechanical complexity. This explains the magnetic pull of the mystery. It offers an escape from a sometimes sterile, fully mapped world into a past that feels alive with unanswered questions. The romantic appeal of lost knowledge is powerful. It suggests that history is not a closed book, but a library with missing volumes waiting to be found. It transforms our ancestors from simple figures in a textbook into enigmatic, capable peers, maybe even mentors, whose lessons are encoded in rock. This desire for a more mysterious, more capable past is not about rejecting science. It is about enriching our sense of human potential. We see this same impulse driving fascination with modern enigmas. The Coral Castle, built single-handedly by Edward, captivates because it replicates the ancient puzzle on a contemporary timeline. The now damaged Georgia, with their cryptic messages carved in granite, were a deliberate attempt to create a modern monolith that would spark speculation for. These are conscious efforts to generate the same aura of mystery, proving that the allure is not in the age itself, but in the combination of immense effort and inscrutable purpose. Ultimately, the stones force a quiet, personal reckoning. In an age where we outsource memory to clouds and physical labor to machines, they represent a tangible, enduring intelligence born directly from human hands and minds. They challenge the unspoken assumption that newer is always better, that our current tools represent the absolute zenith of problem solving. Perhaps the greatest lesson they teach is one of humility, reminding us that achievement is not solely defined by silicon and steel, but also by patience, observation, and a deep, generational conversation with the material world. The enduring fascination is the final, unshakable proof of their success. They were built to last, yes, but more importantly, they were built to make us think, to wonder, and to feel that thrilling vertigo of the unexplained. In that sense, they are not relics at all, but active participants in a dialogue that stretches across centuries, asking us, with every seamless joint, what we believe is truly possible. A single field of study cannot hold the answer to a puzzle this vast. The silent language of stone demands a chorus of interpreters, a meeting of minds from disciplines that rarely speak the same academic language. This is the new frontier, not in the desert or the jungle, but in the collaborative space between geologists and poets, between engineers and oral historians. To solve a mystery woven from material science, celestial observation, and cultural meaning, we must build bridges between the silos of expertise. Imagine where a geochemist places a sample of mortar next to a three-dimensional scan from a laser survey, while a traditional stonemason describes the tactile resistance of andesite under a bronze chisel. This is not a hypothetical scene. It is the necessary methodology for the 21st century. The Society for Interdisciplinary Studies has long championed this approach, convening experts who can ask each other the questions their own fields might never consider. A mechanical engineer can calculate the precise coefficient of friction for a 1,000-ton block on a lubricated limestone track, providing a hard physics framework for what was possible. But it is the archaeologist who must then ask if the historical record shows evidence of such a track being built. The material scientist can identify the exact mineral signature of a stone, tracing it to a quarry 50 miles away, which then allows to map potential transport routes using geographic information systems. This collaborative model has already yielded stunning breakthroughs in other areas of ancient technology. For decades, the durability of Roman concrete was a legend. Modern concrete cracks and degrades within decades, yet Roman harbors have withstood seawater erosion for two. The mystery was only solved when a team of chemists, geologists, and archaeologists analyzed samples at a microscopic level. They discovered the Romans used volcanic ash and lime, creating a mixture that actually self-heals, as seawater reacting with the material forms new minerals that fill cracks. This was not a discovery made in an archaeology department alone. It was born in a materials lab. Similarly, architects and aerodynamicists have used wind tunnel testing on scale models of pyramids, revealing how their shape minimizes wind load and erosion, an elegant fusion of form and enduring function. For the precision stonework Enigma, this means aggressively sharing data. The detailed three-dimensional laser scans of sites like Puma or the should-be open-source digital artifacts, available to any engineer or programmer who might write an algorithm to detect subtle tooling patterns invisible to the human eye. We must also expand our definition of an expert. Beyond the doctorate, there is profound knowledge held in the hands and the stories of communities. Including indigenous knowledge holders is not a symbolic gesture, it is a critical research strategy. In the Andes, master stonemasons from local communities, who still work with traditional techniques, can provide irreplaceable insights into the feel of the stone, the sound it makes when struck correctly, and the practical challenges that are never written in a manual. Their oral traditions may preserve fragments of logistical knowledge or symbolic meanings that contextualize the why behind the precision. A powerful example of this synthesis in action is the ongoing work of the Polish-Peruvian team at. They did not just excavate, they combined rigorous archaeological stratigraphy with architectural analysis and engineering surveys. By meticulously studying the styles of stonework, the tool marks, and the construction sequences, they were able to identify distinct building phases, revealing how the site evolved over time. They could see where repairs were made, where techniques improved, and how the builders adapted to the mountain's topography. This layered understanding turns a static ruin into a dynamic story of problem-solving. The path forward, then, is not a race for a single eureka moment that explains everything. It is a slow, patient, collective endeavor. Each discipline holds one piece of the truth. The astronomer charts the alignment, the geologist identifies the source, the engineer models the stress, the anthropologist decodes the symbol, and the local historian remembers the story. Only when these fragments are brought together, compared, and debated does the full picture begin to emerge from the stone. The final explanation may not be a dramatic revelation of a lost machine, but a deeper appreciation of a lost synthesis, a way of thinking that seamlessly blended art, science, and spirit into a single, enduring act of creation. That seamless granite joint is a social contract written in stone. The precision we marvel at is impossible without a society equally precise in its organization, a civilization capable of orchestrating human life on a scale that still takes our breath away. To build a pyramid was not merely to stack blocks, it was to feed, house, and direct thousands of individuals for decades, weaving their collective effort into a single, immortal gesture. This level of coordination reveals a world of profound social complexity, where the stability of the state was the true foundation for every perfect angle. The first requirement was an immense agricultural surplus. You cannot pull a 100-ton block on an empty stomach. Societies like ancient Egypt achieved this through mastery of their environment, harnessing the annual Nile flood to create predictable, abundant harvests. This surplus food was the fuel for the entire operation, the economic engine that freed a significant portion of the population from farming to become full-time laborers, artisans, and overseers. As geographer has analyzed, the state likely leveraged the natural rhythm of the Nile's inundation. When the fields were flooded and farming was impossible, the state could mobilize a vast labor force, a form of tax paid in work, for massive construction projects. This was not necessarily year-round slavery, but a seasonal, organized duty that benefited from a period when agricultural labor was naturally suspended. The logistics of this mobilization are staggering to contemplate. We are talking about a pre-industrial society managing a supply chain that would challenge a modern corporation. It required a centralized authority with the power to count, to tax, to store, and to redistribute grain on a national scale. Scribes tracked everything, from the number of copper chisels issued to a work gang to the daily bread ration for a quarryman's family. This bureaucracy was the invisible framework, the administrative precision that made the physical precision possible. The social structure was necessarily hierarchical and stratified. At the top, a god-king or a divine elite provided the ideological impetus and commanded the resources. Below them, a class of architects, engineers, and priests translated that vision into geometric reality. Then came the army of specialists, the skilled stonemasons who understood the grain of the rock, the toolmakers who kept the copper saws sharp, the boatmen whose supplies along the river. Finally, there was the vast labor force, doing the brute work of hauling and lifting. But even here, the evidence suggests a more nuanced picture than simple coercion. The excavation of the workers' town at Giza paints a revealing portrait. Archaeologists have uncovered not grim slave quarters, but organized barracks, large communal bakeries capable of producing thousands of loaves a day, and evidence of medical care, including set bones and surgical procedures. Analysis of animal bones shows the workers consumed a diet rich in meat, fish, and beer, a diet that provided the calories for backbreaking labor but also suggests a degree of care and investment in the workforce's health and morale. This was a national project, and participation in it, whether compelled or compensated, likely carried social prestige and a sense of shared identity. The infrastructure supporting the monument was itself a marvel. Permanent quarries were established with their own support communities. Roads were built or waterways improved to move stone. At Giza, a vast artificial harbor was constructed to receive limestone blocks floated from quarries across the river. The project created its own economy, employing not just laborers, but potters to make water jars, weavers to produce ropes, and fishermen to feed the multitude. This brings us to the heart of the social implication. The ability to achieve such technical precision is a direct reflection of a society's ability to achieve social precision, to align the wills and muscles of thousands toward a single, generational goal. It speaks of a shared belief system so powerful that it could justify decades of sacrifice, a cultural narrative that bound the fate of the individual to the glory of the collective and the cosmos. The pyramid was not just the pharaoh's tomb, it was the nation's project, a physical anchor for social cohesion. In this light, the perfect joint becomes a symbol of that social unity. Just as every irregular stone was shaped to fit its unique place in the wall, every individual, from the master architect to the water carrier, had a defined role in the societal machine. The monument's endurance was a testament to the endurance of the order that built it. When we look at these stones today, we are not just seeing a mystery of engineering, we are witnessing the fossilized ambition of an entire civilization, a snapshot of what humans can achieve when we organize ourselves with a purpose that transcends a single lifetime. That level of collective focus may be the most lost technology of all. The flawless joint is a visual language of its own, speaking directly to our sense of order and beauty. While we dissect the mechanics of how it was done, we must not become deaf to this other conversation, the one about aesthetic intention. These builders were not just solving an engineering problem, They were crafting an experience, using stone, light, and shadow as their palette. The visual and tactile perfection was designed to do more than just stand. It was meant to overwhelm the senses, to declare a harmony between human will and the immutable laws of geometry. Consider the play of light on a finished surface. When the sun rises over the Giza Plateau, its rays do not simply illuminate the pyramids, they engage with them. The low morning light rakes across the once polished casing stones, now mostly gone, but in their prime, they would have created sharp, clean lines of light and deep, absolute shadow. This was not a happy accident, it was a calculated effect. The geometric perfection of the form transformed the structure into a colossal sundial and a reflector of celestial glory, its appearance changing with the hour and the season, always asserting its mathematical purity against the soft chaos of the desert. The aesthetic principles at work are both universal and meticulously applied. Symmetry and proportion governed everything, from the grand footprint of a temple to the relationship between individual blocks. Look at the contrast deliberately engineered into the walls of. The central portions of the giant stones are often left with a rough, bossed texture, a testament to their raw, mountainous origin. Yet their edges, the joints where they meet their neighbors, are planed to a smooth, seamless finish. This creates a powerful visual tension, a dialogue between the wild, natural state of the rock and the absolute control exerted upon it by the craftsman's hand. It reminds the observer that this order was wrested from chaos, a permanent victory of culture over nature. This artistry extended to the integration of the structure into the landscape. Does not sit on the mountain, it is of the mountain. The terraces mimic the contours of the peaks, and the buildings are arranged to frame sacred summits in their windows and doors. The stonework itself, using the local granite, makes the city feel like a natural outcropping that has been meticulously organized. The builders were listening to the land and composing their work in response. The psychological effect of this environmental and technical harmony is profound. To stand before a wall where not even a blade of grass can grow between the stones is to feel a deep, instinctual sense of order. It communicates permanence, stability, and a kind of transcendent truth. In a world of uncertainty, here was something that refused to decay, something that obeyed a higher, more perfect set of rules. This was architecture as a moral statement, where physical flawlessness implied spiritual and cosmic flawlessness. A masterful example of this principle, where precision served an artistic vision above all, is the Parthenon in Athens. To our eyes, its columns appear perfectly straight, but they are not. The architects employed subtle optical corrections called entasis. Each column swells slightly in the middle and leans inward, while the platform itself curves upward at the center. If built with rigid, geometric straight lines, the building would have looked distorted to the human eye, the columns appearing to bend outward and the platform seeming to sag. By introducing these calculated imperfections, the builders achieved the illusion of perfect straightness and stability. This reveals a breathtaking priority. The experience of the observer was paramount. The truth of the measurement was less important than the perceived truth of beauty and balance. This brings us to the heart of the aesthetic dimension. The ancient master was a hybrid figure, an engineer-artist. The flawless fit was not merely a technical benchmark, it was the ultimate artistic expression. It represented the point where material yielded completely to intention, where the countless hours of labor vanished, leaving only the serene, silent result. The beauty lies in that erasure of effort, in the presentation of a puzzle so perfectly solved that it appears effortless, a permanent testament to a moment when humanity and stone spoke in a single, harmonious voice. The most honest witnesses to this ancient craft are its failures. Scattered across the globe, frozen in the very act of creation, lie the unfinished sites. These are not monuments to completion, but invaluable time capsules, offering a raw, uncensored snapshot of the builder's methods caught mid-stride. Here, the process is laid bare, with tools abandoned beside partially liberated stones and the ghosts of ramps still etched into mountainsides. To walk through one is to step onto a construction site where the workers have just stepped away, leaving their secrets in plain sight. Perhaps the most instructive of all is the unfinished obelisk in the granite quarries of Aswan, Egypt. Still clinging to the bedrock, this colossal needle, which would have been the largest ever erected, is a textbook of quarrying technique. Around it, you can see the clear, straight trenches cut by workers wielding nothing but stone balls. These dolerite pounders, some still found nearby, were used to bash a channel directly into the granite. Teams would swing them in rhythm, pulverizing the rock grain by grain. The trench reveals the method's brutal simplicity and its staggering limitation. It is a technique of immense force but almost no finesse, perfect for separating a block, but incapable of creating the polished surfaces we see on finished works. This disconnect is the site's silent testimony. The rough work of liberation is visible, but the magic of refinement is not. At the opposite end of the scale, the quarry at Baalbek shows the audacious beginning of a megalith. Beside the famed stone of the pregnant woman, you can trace the method for undercutting a 1,650-ton monster. The builders did not simply pound from above. They carved deep, narrow channels around the block's perimeter, then dug horizontal tunnels beneath it, leaving a series of stone pillars as temporary supports. The final step would have been to break these pillars, allowing the block to settle onto a prepared bed for transport. This reveals a sophisticated stage plan and an intimate understanding of stress and leverage, even for a stone they never moved. High in the Peruvian Andes provides in logistics. Here, giant red porphyry blocks were dragged from a quarry across a valley and up a steep mountainside. The evidence is preserved in the landscape itself. You can still follow the causeway, a prepared road, and see the massive stone ramps built to haul the blocks to the top of the temple platform. At the base of these ramps lie several enormous stones that never made the final journey, permanent waypoints in an interrupted effort. They show the system in action, a clear path from quarry to construction site, demanding immense communal effort and ingenious engineering to conquer gravity itself. Archaeologists like Richard, who meticulously documented Egyptian quarries in the 19th century, use these sites to reconstruct the ancient stonemason's step-by-step process. The sequence becomes clear. First, quarrying, separating the stone from the earth using trenches, wedges, or undercutting. Second, rough shaping, knocking off major protrusions to make the block manageable. Third, transport, moving it to the site via ramps, sledges, or waterways. Fourth, and most mysterious, the fine fitting and polishing, the stage that leaves the fewest marks on the unfinished stones. The clues are often in the small details. Look for the bosses, those rounded knobs left on the faces of many partially worked stones from Egypt to Peru. These were not decorative, they were practical handles. Ropes could be tied around them for maneuvering the block into its final position. Only after the stone was perfectly seated would these bosses be carefully chiseled away, leaving the seamless surface we admire. This tells us the fitting happened on site, a precise, final adjustment. Different tools leave distinct signatures, and unfinished sites are of these marks. Alongside the pitted trenches from stone pounders, you can sometimes find the straight, shallow grooves of copper saws, the circular depressions from tubular drills, or the smooth, curved scoops that defy simple explanation. A remarkable window into this world is the Roman imperial quarry at Muon in Egypt's eastern desert. Here, amid the stark mountains, half-carved columns and capitals litter the ground, abandoned when an order was changed or priorities shifted. Even more telling are the ostraca, thousands of pottery shards used as notepads. These informal memos record the daily life of the workforce, requests for tools, reports on work progress, and even complaints about the quality of the wine rations. They give names and voices to the anonymous laborers and foremen, revealing a highly organized, bureaucratic operation run with military efficiency. These unfinished works are indeed like paused videos of ancient technology. They show us the first 90% of the process with startling clarity, the brute force, the logistics, the organization. Yet they also deepen the mystery of the final 10%, that leap from a shaped block to a perfected, seamless marvel. The tools left behind can explain the rough cut, but the finished surfaces whisper of a finer touch, one that has left no trace in the abandoned quarry. The next chapter of this story will be written not with chisels, but with sensors. As we stand before these silent monuments, the most exciting question is no longer what we have lost, but what we are about to find. The future of this mystery lies in our ability to ask the stones new questions, using technologies that listen for answers without leaving a single mark. This is the era of destructive investigation, where the goal is to understand the structure by seeing through it, not by taking it apart. At the forefront is a technique that sounds like science fiction, Muon tomography. It harnesses cosmic rays, subatomic particles that constantly rain down from space, penetrating deep into solid matter. By placing sensitive detectors around a structure like the Great Pyramid, scientists can map how these muons are absorbed. Denser areas, like solid stone, block more particles, while voids allow more to pass through. This creates a three-dimensional X-ray on a monumental scale. The Scan Pyramids project has already used this method to reveal a startling discovery, a large, previously unknown void above the Grand Gallery. This is not a small crack, but a space the size of a cathedral hall, a hidden chamber that has waited over 4,500 years to be found. What might it contain? The answer could be nothing, or it could be everything, a time capsule of tools, texts, or ritual objects that finally explains the how and why. Promises to map the entire internal structure of the pyramid and other megaliths, revealing construction sequences, hidden chambers, and internal stresses we never knew existed, all without moving a single stone. Alongside this cosmic vision, we have the power of microscopic insight. Portable X-ray fluorescence, or PXRF, is a handheld device that looks like a futuristic scanner. When held against a stone surface, it bombards the area with X-rays, causing the atoms in the material to fluoresce, emitting a unique spectral signature. This allows scientists to determine the exact elemental composition of the rock in seconds. The implications are profound. By analyzing stones at a site like Puma, researchers can match each block to its specific quarry, tracing a precise logistical map of ancient industry. More tantalizingly, it can detect chemical residues. If an ancient builder used a plant-based solution to soften stone, even a trace amount of organic compounds or unusual elements might remain locked in the microscopic pores of the rock. A PXRF scan could, in theory, detect the ghost of that recipe, the chemical fingerprint of a lost technology. This same principle applies to residues of ancient abrasives, binders, or even the metal alloys used in long-vanished clamps. We are moving from studying the shape of the stone to analyzing its very chemistry, searching for the invisible fingerprints of the hands that shaped it. The digital models we create are becoming more than just records. They are becoming intelligent partners in discovery. Artificial intelligence, trained on vast libraries of tool marks and wear patterns, can be set loose on a three-dimensional scan of an ancient wall. It can scan millions of data points, identifying subtle, repeating patterns that the human eye would never see. It might distinguish between the stochastic chaos of natural weathering and the consistent, directional signature of a guided saw. It could categorize different types of chisel marks, potentially linking them to specific tools or workshops. This AI-assisted analysis could one day read the surface of a stone like a forensic scientist reads a crime scene, reconstructing the exact sequence of tools used and even the angle at which they were held. Furthermore, advanced physics simulation software allows us to test theories in a perfect, risk-free digital sandbox. Want to know if a team of 200 men could pivot a 1,000-ton block using a specific lever configuration? Build a digital model, input the known properties of wood, rope, and stone, and run the simulation. The software will calculate the forces, show points of failure, and reveal whether the idea is physically plausible. This turns speculation into testable hypothesis, narrowing the field of possible explanations with mathematical rigor. The The search is also expanding geographically, beyond the boundaries of traditional archaeology. Citizen science initiatives are harnessing the power of global curiosity. Platforms allow anyone with an internet connection to examine high-resolution satellite imagery, searching for geometric patterns, straight lines, or rectangular shadows that might indicate a buried structure. This crowdsourced approach has already led to the discovery of new archaeological sites, from potential Viking settlements in North America to lost cities in the Amazon. For every famous site we study, there may be 10 more waiting to be found, each one holding a missing piece of the puzzle. Final key may still be physical, lying in the sand or the jungle. The potential discovery of a new text, a detailed artisan's journal on a clay tablet or a papyrus scroll, remains the holy grail. While no such manual has been found for the pyramids, the chance always exists. An intact tomb of a master builder, buried with his tools and his plans, could rewrite history in a single afternoon. Every new excavation, conducted with modern stratigraphic care, brings that possibility closer. The mystery of the precision stonework will likely not surrender to a single eureka moment. Instead, it will gradually dissolve under the relentless, angled light of new technology. Each scan, each chemical analysis, each simulation adds a data point, tightening the circle of possibility. We are learning to converse with the past in a new language, one of particles, pixels, and algorithms. The stones have kept their secrets but for the first time, we are building tools that can listen to whispers we never knew were there. The future of this ancient mystery is a collaborative technological archaeology, a slow and patient assembly of proof that may one day allow us to understand, not just how they built, but to hear the quiet confidence in the mind of the master who knew the stone would hold, perfectly, for eternity. Theories dissolve into dust the moment you place your hand on the stone. All the data, the debates, the digital models, they cannot prepare you for the physical presence of these places. To stand in their shadow is to undergo a quiet, personal, where the mystery ceases to be an abstract puzzle and becomes a visceral, bodily truth. The journey shifts from understanding with your mind to knowing with your senses. The first shock is always scale. No photograph, no drone shot can communicate the sheer, overwhelming mass of a block that towers over you, a single piece of rock that weighs more than your house. You feel it in your chest, a subtle pressure, a humbling rearrangement of your place in the world. Then comes the touch. On a cool morning at or in the dry heat of Giza, pressing your palm against a joint that has held is an act of communion. The stone is surprisingly cold, even in the sun, and its surface is not rough, but almost silken from centuries of weather and the builder's own obsessive polishing. You trace the seam with your fingertips, searching for the gap that logic says must be there, and finding only seamless rock. It is a silent, tactile argument against everything you thought was possible. To walk these sites is to navigate a landscape of intention. Climbing the steep, uneven stairs of the Pyramid of the Sun is not just exercise, it is a physical reenactment of ascent. With each step, your breath shortens, the city's grand geometric plan unfolds below, and you become acutely aware of the alignment beneath your feet, the way the avenue points toward a sacred mountain on the horizon. At dawn, when the crowds are thin, the low sun casts long, sharp shadows that make the geometry sing, revealing lines and angles invisible at midday. This is when the site speaks most clearly. The same is true in the echoing passage of the Great Pyramid. The climb up the Grand Gallery is a constricted, sloping journey into the Earth's heart, culminating in the stark, startling space of the King's Chamber. Here, the silence is absolute, a thick, palpable quiet. You look up at the colossal granite slabs overhead, each weighing over 50 tons, and feel their mass in a way that is almost audible. The chamber's perfect proportions, its precise orientation, create a strange sensation, as if the space itself is charged with a silent, focused purpose. You are not in a tomb, you are inside a machine made of stone, and its function is to last forever. To have this experience fully demands a little planning. The practicalities matter. Visit at opening time or late afternoon to avoid the crush of crowds and witness the transformative light of sunrise or sunset, when celestial alignments often reveal themselves. If you can, engage a knowledgeable local guide. A good guide does not just recite dates, they point to the subtle details you would miss, the odd protrusion on a block that was a lifting boss, the slight concavity of a wall designed for earthquakes, the single stone in a facade that is of a different, faraway quarry. They help you read the story written in the rock. Most importantly, approach as a respectful guest, not a conqueror. These are not amusement parks, they are fragile sacred spaces. Do not climb where it is forbidden, touch gently if allowed, and leave no trace. Your presence is part of the site's ongoing life, and how you behave either preserves the mystery for the next visitor or slowly erases it. The emotional reaction is universal, yet deeply personal. People speak of a profound sense of smallness, not of insignificance, but of being a brief moment in a vast, continuous story. There is awe certainly, but also a curious intimacy. As you study a perfectly fitted joint, you experience a flash of connection to the individual who made that final cut thousands of years ago. You are separated by an abyss of time, yet united by the shared perception of this line, this angle, this pursuit of perfection. It is a silent conversation across centuries. This personal encounter is the ultimate answer the stones offer. It moves beyond the frantic question of how did they do this and settles into the deeper, more resonant question of why. Why did cultures across the globe dedicate generations to such an impossible task? Standing there, feeling the cool granite and seeing the shadow of a pyramid stretch across the desert, you feel the answer. It was not for utility alone. It was a declaration. A statement of belonging to the cosmos, of creating order from chaos, of speaking to the future in a language that would never be forgotten. The precision was their voice, and in the quiet of these places, if you listen closely, you can still hear its echo, inviting you not just to solve but to wonder. The journey through these silent, staggering stones leaves us not with an answer, but with a richer, more beautiful question. We have walked the seamless ramparts of, and felt the impossible smoothness of the boxes. We have grappled with the tool conundrum, marveled at the logistical nightmares of Baalbek, and listened to theories that stretch from acoustic resonance to forgotten chemistry. We have seen how this precision served water, withstood earthquakes, mapped the stars, and encoded the deepest beliefs of entire civilizations. The evidence is a mosaic, and every piece we examine reveals another layer of the mystery. These structures do not whisper a single secret. They speak in a chorus of contradictions to our modern assumptions. They challenge the very timeline of progress, suggesting peaks of human achievement that rise in unexpected places, then fade into silence. The key takeaway from this exploration is not a tidy solution. It is a profound respect for the complexity of the puzzle itself. These are not problems to be solved and filed away, they are permanent invitations to wonder. They stand as eternal counterpoints, written in granite and limestone, asking us to reconsider what we believe is possible with patience, observation, and collective will. The past, as we have seen, is not a simple, linear story of primitive to advanced. It is a rich and tangled tapestry, and we have only just begun to trace its most dazzling threads. The science fiction writer Arthur C. once observed that any sufficiently advanced technology is indistinguishable from magic. To our eyes, conditioned by engines and computers, the work of these ancient masters still holds a shimmer of that enchanting, inexplicable quality. It is a magic born not of wands, but of wisdom, of a deep, generational conversation with the material world that we have largely forgotten how to have. So let this not be an end, but a beginning. Let the sight of a perfect joint inspire you to look deeper, to question the standard narratives, and to see the landscape of history as a place alive with mystery. We want to hear your voice in this ongoing conversation. What site captivates you the most? Which theory resonates? Or what idea have we not yet considered? Share your thoughts and discoveries in the comments below. If this journey into the enigmatic craftsmanship of our ancestors has sparked your curiosity, please subscribe. We are dedicated to exploring the edges of history, science, and human potential, to bringing you more content that challenges what you think you know. Thank you for joining us on this exploration of stone and shadow. Keep looking, keep questioning, and above all, keep wondering.